All right. Dear all, welcome to the Forum on Robotics and Control Engineering. My name is Tansel, Yucelen, and I am an assistant professor at the Department of Mechanical Engineering of the University of South Florida. At my university, I am also director of the Laboratory for Autonomic Control Information and Systems, or shortly LACES. With the support from my university, I am very proud today to host Dr. Liberzon from the UIUC to participate in our live seminar series on control systems through the FoRCE. So a few words about the FoRCE. Basically, FoRCE is dedicated to provide free, high-quality outreach events and online seminars to reach broader robotics and controls engineering communities around the globe. To support our mission, we periodically invite distinguished lecturers like Professor Liberzon to give talks on recent research results related to robotics and control engineering. As such, FoRCE aims in connecting academicians and government and industry researchers and practitioners with each other through cross-cutting research and education discussions. We truly hope that you will enjoy all the FoRCE events and find them highly valuable to your own research interests. I am almost done, but let me mention a few words about WebEx before I formally introduce Dr. Liberzon. During the presentation, we are all muted, and so if not, please mute yourself. We'll take questions after the presentation. You can do this by virtually raising your hands through WebEx, or you can simply unmute yourself. And for your information, session is being recorded to be posted to the FoRCE website. And if you do not wish to have your voice included, you can use the chat box. You can send the question to the general or everyone or to me. Then I can read these questions to Dr. Liberzon. So first of all, before I formally introduce Dr. Liberzon, let me pass the ball to him. All right. I am now changing the presenter. So again, I am very proud today to have Dr. Liberzon. He was born in the former Soviet Union in 1973. He received a PhD degree in 1998, supervised by Prof. Roger Brockett of Harvard University. Following a postdoctoral position in the Department of Electrical Engineering at Yale University from 1998 to 2000 with Professor Stephen Morse, he joined UIUC, where now he's a professor in the Electrical and Computer Engineering Department and the Coordinated Science Laboratory. His research interests include nonlinear control theory, switched and nonlinear switched and hybrid dynamical systems, control with limited information, and uncertain and stochastic systems. He is the author of the books Switching in Systems and Control and Calculus of Variations and Optimal Control Theory, A Concise Introduction. His work received several recognitions, including the 2002 IFAC Young Author Prize and 2007 Donald P. Ackworth Award. He delivered a plenary lecture at the 2008 ACC American Control Conference. He is a fellow of the IEEE and IFAC and an editor for Automatica on the nonlinear systems and control area. So for all of you who are here live for the presentation of him, I first would like to thank Dr. Liberzon for participating in our forum. And Dr. Liberzon, I already passed the ball to you, and whenever you are ready, we are ready for your talk.
Thank you, Tansel. So just to make sure everything's still working.
Everything is perfect. We can see you. We can see your presentation. Everything is, your sound is perfect. Everything is perfect.
Okay, thanks. I'll go ahead and start. And thank you very much, Tansel, for inviting me, for hosting and organizing this seminar. And I want to thank all of you for joining, taking the time from your busy week. We should congratulate ourselves that the CDC deadline has passed, hopefully successfully, for all of us. And I thank you for coming to listen to my presentation today. So let me now change to the format where you can just see my slides. Okay. So, as Tansel mentioned, I'm going to talk to you about nonlinear observer design. I'm going to talk about observers that have a robustness property with respect to measurement errors. I'm going to explain what I mean by this. And after presenting some theoretical results about the design and analysis of such observers, I'm also going to discuss a few applications in control design and also in system synchronization. So let me go to my general motivation first before I get to something more specific. So the general motivation comes from taking into account information flow in control systems. So imagine that this is a feedback loop, that maybe this robot represents a plant being controlled, and this computer represents a controller where the controller is computed and control input is sent to the plant. But also in the feedback loop, there are information processing devices represented here by perhaps a digital camera that's collecting measurements, and maybe this wireless medium in the left path through which the control signal is being sent to the robot. So in such situations, it's important, in addition to classical control theoretic considerations, it's important to take into account these information processing devices in the feedback loop and the effect that they have on the control design. And this becomes especially important when this one feedback loop is just a small portion of the overall network control system, with many feedback loops sharing the network and sharing the information resources. So in such situations, several important issues arise. You may have poor sensing in the system for either cost reasons or physical reasons. It may be impossible to install sensors with resolution that's desirable in all the places that you would like. You may have limited communication capacity because the bandwidth in the system may be limited, or, as I said, shared by several feedback loops. Also, even if you're able to send a lot of information through the channel, you may not want to send more than absolutely necessary because of security considerations. And what I said about sensing also applies to actuation. So your actuators may be limited to something that's very simple, that maybe is event-driven, take only finite remaining values. And above all, at least for me, there is a great amount of theoretical interest that to address these problems and to develop a comprehensive theory that captures both the control design and the flow of information in the system. There is a lot of theoretical interest that drives this research, and this area has been quite active over the past few decades. So what I am going to focus on in this talk is that this limited information that I mentioned leads to all sorts of errors. These could be, for example, quantization errors, errors resulting from analog to digital conversion, delays, and so on. And then when we talk about developing control algorithms, we need to make sure that these control algorithms have appropriate robustness to these errors. So that is basically what I'm going to be addressing in this talk. Now, moving a bit closer to the specific topics that I'll be discussing, I will be talking about observer-based feedback control, observer-based output feedback. And this is a diagram that represents the plant, the controller, they're connected to the sensors, this channel, which may introduce some errors due, for example, to quantization and other aspects I mentioned. Then I have an observer here, which generates an estimate of the state of the plant, and this estimate is fed to the controller, which is connected in feedback with the system. And the errors propagate through the system as shown by these red arrows here. So if you have errors affecting the information coming out of the sensors, these errors in turn affect the ability of the observer to produce a good estimate of the plant. And the errors affecting this estimate of the plant, which I denote by x hat, in turn affect the ability of the controller to provide satisfactory performance to the feedback loop. And so this is the issue in front of us. And if you look at the literature, I would say that relatively little is known about the effects of the error propagation on the right side of the diagram. So what I mean by that is that there's been quite a bit of research about designing robust controllers robust to various errors, disturbances, but there's been relatively less research about designing observers that have robustness in a similar sense to errors and disturbances affecting sensor measurements. So we're interested in both here, but there is more of a gap to be filled here on the right for the observer design, and that's why I'll be focusing a bit more on that part of the story in this talk. And the main technical tool that I'll use will be input to state stability, or ISS, which in my mind provides a good framework for characterizing the robustness or graceful degradation of performance, if you will, in response to errors present in the system. I will talk about ISS, I'll provide a quick review, and then this is something that will be used as a technical tool throughout the talk. So this is my talk outline. As I said, I'll give a brief overview of ISS. For those of you not very familiar, this will serve as a quick introduction, but I'll also provide a technical result, a new technical result, which will have to do with the so-called asymptotic-ratio characterization of ISS. After that, I'll move to the main part of the talk, which will be about designing observers robust to measurement disturbances. I will talk about the formulation of the problem, also some LYAPUNOV-based conditions for checking robustness of the observers. I will apply this to the setting of output feedback control that I had on the previous slide. And then I'll discuss two applications to problems in synchronization under measurement error. So let me, before I go to the technical details, let me mention the references on which this work is based. And I'd like to acknowledge my co-author, Professor Hyunbo Shim from Seoul National University in Korea, with whom we wrote a couple of papers that serve as a basis for much of this talk. The first paper here is a technical note in transactions in 2015, which talks about this asymptotic-ratio characterization of ISS. And then a longer paper in transactions the following year talks both about the observer design that I'll present and also about its use in control design. And there's also an earlier paper that appeared in CDC several years before that. And then as applications to robust synchronization, I will talk about two examples. One is the work that we are currently doing with my colleagues at Illinois. We actually just 3 days ago submitted a CDC paper on this. It has to do with applications to synchronizing electric power generators. And then the second example that I'll present is very work done with my colleagues in St. Petersburg, Russian Academy of Sciences, on an example of a Lorentz chaotic system. So let me go to the first part, which is a quick refresher about input to state stability. This is a notion that was introduced by Eduardo Sontag in the late 80s and has been very influential in nonlinear system theory as a tool for capturing and studying the effect of disturbances in nonlinear systems, particularly nonlinear control systems. So let's consider a system of this form. X dot equals f of x and d. So here x is the state, d is an external disturbance. And by definition, we say that the system is input to state stable, or ISS, if its solutions satisfy the following estimates. I will take a minute to go through this and explain what this means. So first of all, let's look at the function gamma here. So this is a so-called class K infinity function. So it's a nonlinear gain function. Class K infinity functions are functions whose graph look like this orange curve here on the right. So it starts at 0 and continuously increases to infinity. And the argument here is the supremum norm of the disturbance on the interval from time 0 to current time. So this is one of the two terms in the summation. The other term, the first term, captures the effect of initial conditions. The function beta is a function of two arguments. It's class K infinity in the first argument, so it's increasing with the size of the initial condition, and it decreases to 0 in the second argument, which is time. Okay? So if you were to imagine that only the first term is here and the second term is not here, this is actually the usual global asymptotic stability of the system in the absence of the disturbance. But the second term captures, via this nonlinear gain function gamma, the effects of the disturbance. So just like for standard Lyapunov asymptotic stability, input to state stability has Lyapunov characterizations in terms of Lyapunov functions that people have worked out several versions of over the years. So I'll mention two. One way to write the ISF Lyapunov function condition is that there exists a function v satisfying the usual properties, positive definite, radially unbounded, continuously differentiable, which satisfies this property encoded by this implication. So the derivative of v along solutions to the system is negative, not everywhere, but it's negative when the size of the state is large enough compared to the size of the disturbance as given by some gain function rho. Rho is a function of class K infinity. In fact, this rho function is directly related to the gamma function, which we usually call the ISS gain. They're not the same, but they're easily computed one from the other. So whenever the size of x exceeds rho of the norm of v, v should decrease along solutions of the system. You can also, and it turns out that that's equivalent, write this as this dissipation type inequality where the time derivative of the Lyapunov function is upper bounded by a negative term that depends on the state plus a positive term that depends on the disturbance. So all of these Greek letters denote class K infinity functions. And here on the right-hand side, you see this tension between the decay that's driven by the size of the state and the possible growth that depends on the size of the disturbance. So both of these are equivalent to each other and equivalent to the input to state stability property of the system. And simple examples can be used to show that if the system is globally asymptotically stable in the absence of the disturbance, when the disturbance is set to 0, this does not imply ISF. You can look at an example like this, where if I turn off the disturbance, I get x dot equals minus x, which is a nice exponentially stable system. But if I take the disturbance to be equal to 2, solutions increase. And I can have even more drastic behavior when I replace x here with x squared. The solutions may blow up in finite time, may have finite escape time, even for disturbances that approach 0 asymptotically. So it's really not sufficient at all for the system to behave nicely under 0 disturbances. ISS provides a tool for capturing nice or graceful degradation of performance under bounded or small disturbances. I will quickly mention this asymptotic ratio version of the ISS Lyapunov function condition because we will use it later for observer design. So here I'm just copying the two ISS Lyapunov function conditions that I had before. And I, by definition, say that V is an asymptotic ratio ISF Lyapunov function if it satisfies the following dissipation inequality. So here, unlike in inequality 2, the second term depends both on the state and on the disturbance. And I have several conditions that I'm requiring from my functions, which are not very important right now to focus on. But the main one, and this is what motivates the name asymptotic ratio, is that if you divide G by alpha 3, so G is the positive term, alpha 3 is negative term, the limit superior of this as the first argument increases, and the first argument really is the norm of the state. For a fixed size of the disturbance, this ratio should be less than 1. So that's asymptotically, this ratio should be less than 1 when you fix the disturbance magnitude and increase the magnitude of the state. And in case, by the way, in case you're wondering why it's alpha 3, well, I'm following the notation that's used in our papers, and the reason it's alpha 3 is because we typically have alpha 1 and alpha 2, which provide lower and upper bounds for the Lyapunov function. I'm just not using and then just not showing those two functions on the slide. So what we proved in the paper with Hyun-Bo is that ISS is equivalent to the existence of this type of asymptotic ratio ISS Lyapunov function. And the proof of sufficiency follows the this well-known dissipation inequality 2, which is stronger than asymptotic ratio characterization. But the challenge is improving the converse, and that requires us to construct the function rho as in inequality 1, which gives us the ISS gain. And that's where all the effort in proving this result is concentrated. Okay, so just a quick example. This is something that you may want to work out more slowly later, but if I consider the simple scalar system and I take v to be just half x squared, I have this expression for the derivative of v, and I can manipulate it to this, and then I note that this is my dissipation, this is my minus alpha 3, and this is my g of x and v. And if I were to divide g by alpha 3, I would get this ratio, d squared over 1 plus d squared, which is less than 1. And the second term, when divided by x squared, would go to 0. So the asymptotic ratio condition is satisfied. On the other hand, I invite you to try to prove ISS of the system using more standard properties, like properties 1 and 2 listed on top of the slide. It is possible, but it I think, is more challenging than using the asymptotic ratio characterization. The trade-off here is that we don't get any information about the ISS gain from this asymptotic ratio Lyapunov function. Now, having hopefully warmed you up to this notion of ISS and having recalled the Lyapunov characterizations of ISS, let me now go to the main part, which is the observer design. So the robust observer design problem, in general terms, is formulated as follows. I have a plant. I have sensors that measure the output Y, which is corrupted by disturbance. So the formulas are here. Note that in the picture, the disturbance enters additively, but this need not be the case. It can enter in a general way as well. Then I'm trying to build an observer which accepts as input the measured output as well as the control input of the plant, and the goal is to produce the estimate x hat of the state. So I have formulas for the observer here. The state of the observer may have the same dimension as the state of the plant, in which case we call it a full order observer. Otherwise, if the state dimension is v, m is smaller than the state dimension n of the plant, we call it reduced order observer. And then you look at the error between x and x hat, we call it E, state estimation error. And the robustness issue, just like I had similar examples earlier illustrating that asymptotic stability under zero disturbances does not imply ISS, you can construct examples where the observer behaves well when there's no disturbance. It asymptotically correctly estimates the state, but the estimation error goes to infinity even when a very small disturbance D is present. So that's the robustness issue, is to characterize. First, we need to define what robustness property we want to have from the observer. So here I'm just copying the equations that I had before. You don't have to go through them. They're just here for your reference. And there's a natural ISS-like robustness notion that people have considered before. In our work, we call it GDES, for disturbance to error stability. As the name suggests, it's very much in the spirit of ISS. And we call the observer GDES if the estimation error satisfies this ISS estimate with respect to the disturbance. So something looks very standard if you take ISS notion as a benchmark. And several known conditions for this exist. So Sontag, Wong, and David Angeli worked on this. However, as is noted in these papers, and as evidence of these conditions, these are quite strong. So this property of GDES is quite restrictive. It's not very easy to obtain it for even classes of systems for which asymptotic observers are well known to exist and how to construct them. And another drawback of this GDES notion is it's coordinate independent, in the sense that in one coordinate system you may have it satisfied, but if you apply a change of coordinates as given by this function phi, the diffeomorphism on our state space, then you may lose this, so that one does not imply the other. So what we'd like to do is have some condition for robustness that is easier to verify and also enjoys coordinate independence. And it turns out that the path towards formulating such a condition, or a path towards it, is to impose disturbance to error stability not globally, but only as long as the state and the input are bound. So I will elaborate on this, but the basic motivation is that eventually you're going to connect your plant with a controller, which is hopefully going to keep the state bounded. And so maybe ultimately we're not too concerned about how the observer behaves when the plant state is very large and is escaping to infinity. We would be happy if the observer behaves well as long as the plant state is kept bounded by bounded control. So that sounds usually reasonable, and that's the direction we're going to take here. So for this purpose, we'll weaken the definition to the so-called quasi-disturbance to error stability, or QDS. So for the same equations for the plant and the observer, we say the observer is quasi-DES if the following holds. So here we're tweaking the DES definition in the following way. We say that for every positive constant k, there should exist functions beta and gamma, which depend on this k, such that the ISS estimate, the same as I had before, holds as long as both the control input to the plant and the state of the plant are upper bounded by k. In other words, if you give me a ball or any compact set in which your state and control input live, I should find a pair of functions beta and gamma for which the ISS estimate in the green box holds. You give me a larger set, I may have to change my beta and gamma, but I should be able to find a pair of these functions for any compact set. However, I'm not asking that a global pair beta and gamma exists that capture all values of x and u. So for example, again, this is something that you may need to trace the calculations more slowly later. I'm just going a bit fast through this. But for this plant, with the output being just x plus the disturbance d, if you design a scalar observer, which is essentially just a copy of the plant, then these would be your aerodynamics. And you can check that because x and u appear in these two last terms on the right-hand side, you can check that this observer is quasi-DES. So for any compact range of values for x and u, this is ISS from disturbance to error, but it's not globally DES. So it suggests that it's much easier to look for quasi-DES observers than it is for DES observers. And you can also show that the quasi-DES property is invariant to coordinate changes, because essentially what was causing DES not to be coordinate independent was the behavior at infinity, which we are somehow eliminating here. So from this point on in the talk, I want to give you, illustrate conditions for how this robustness property of observers can be checked. And for this, I choose to focus on the case of reduced order observers, which means that it gives me some special structure under which it's going to be easier for me to illustrate the main idea. In our transactions paper, we also cover the more general case, which includes the full order observers, but the details there, I think, are a little bit perhaps more complicated to quickly present in a seminar. So let's look at this. We can treat that as an example. So reduced order observers for a plant with a specific structure like this. So after possibly coordinate change, I assume that the plant state is split into two groups, X1 and X2. And X1 is the output, except that it's affected by an additive disturbance. And I have some general right-hand side here, F1 and F2. The observer that I build, it's a reduced order observer. So I don't need to build an observer for the first component of the state because that is statically measured with my sensor. So my estimate X1 hat will be just Y. And for estimating X2, I'm going to build an observer, which in this case will be a copy of the dynamics of X2. So this is my reduced order observer, and X2 hat, which is V, is the estimate of the second portion of my state. So let us first think what happens if I were to remove the disturbance. So the disturbance is not there for now. I look at the error, the estimation error, which is the difference between V and X2. And let's suppose that I have some error-dependent Lyapunov candidate function V of E. If I differentiate it, I will have this expression. So here, with these red and green colors, I'm encoding the mismatch between, so in red here, this is V, which is X2 plus E. This is in the observer dynamics. In green, this is X2 from the plant's dynamics. Otherwise, the other arguments are the same. So, you know, what I'm going to assume is that we know how to construct an asymptotic observer. That is an observer which makes the error E go to 0 when the disturbance is not there, right? So here I'm focusing on building a robust observer. So I assume that I already have available to me an observer that acts as a static observer when there is no disturbance. So I'm going to assume that I have that, and this can be tested by this Lyapunov function V. So I'm assuming that this right-hand side here is negative, definite, in the magnitude of the error. So in other words, I'm assuming that this is less or equal to some minus class K infinity function of the magnitude of the error. Okay, I'm going to proceed under this assumption. Now I'm going to put back the disturbance and take the same Lyapunov function and differentiate it along the solution of the error dynamics. And now I'm going to have another place where the arguments don't match. The Y here in red is X1 plus V, and it no longer matches the green X1 in the plant dynamics. So I can use the triangle inequality to split it into two expressions. And now the first one is exactly what I had before, which is assumed to be upper bounded by some negative function that's dependent on the magnitude of the error. And then I have this new term to deal with, which is due to the presence of the disturbance. And I'm going to assume, as is fairly standard in this context, that the gradient of V is upper bounded by some other class K infinity function, alpha 4 of the norm of E. And now this expression here essentially depends on the disturbance V. And so if I fix some K, positive constant, and if I take the state and the input to be in the ball of radius K, then this difference will be upper bounded by a function of just the disturbance. And so then if I combine the two, I will have this upper bound for V dot. And I stress again that this does not hold globally, but it holds only when both the size of the input and the size of the state are upper bounded by K. So for any K, I can find a function phi sub K for which this holds. So now when we look at this differential inequality for our candidate Lyapunov function, I can recall now the asymptotic ratio condition that we talked about before. So I need to have that when I take the positive term on the right-hand side and divide it by the dissipation term, this has values asymptotically less than 1 when R, which is the argument in alpha 3 and alpha 4, which is the size of the error, goes to infinity for fixed size of the disturbance. And there's various ways of checking this. For example, an easy sufficient condition for this is that the ratio of alpha 4 to alpha 3 is asymptotically tending to 0 as R goes to 0. Then it's easy to see that this condition on the left is satisfied. And an easy way to test for that in turn is to look for a function alpha, which is class K infinity, such that this inequality holds. So this means that the ratio of alpha 4 to alpha 3 is less than 1 over alpha. So alpha is increasing, so 1 over alpha is decreasing to 0. And if you have this, then you can factor alpha 4 out of the right-hand side of V dot, and you get this expression here for V dot. And this is less than 0 when E is sufficiently large as compared to the disturbance D. So if you go through this calculation, this actually lets you estimate the ISS gain, because the function that appears here is directly related to the ISS gain. But you can only do that if the function alpha is available. In other words, the asymptotic ratio condition here gives you a certificate that the observer has the quasi-disturbance-to-error stability property, but actually estimating the ISS gain depends on the knowledge of these functions that I have in these calculations that I sketched here. Okay, so now having covered the basic idea of what we mean by robust observer and what may be LYAPUNOV type sufficient conditions for it, in the remaining 20 minutes or so, let me talk about applying this idea to control design and later to synchronization. So for output feedback control, let's revisit this diagram that I had before. So let's put in some formulas in these boxes. So I have a nonlinear system with state X and input U. I have some sensor measurements giving me the output Y, which is affected by disturbance D. I have an observer here, which I assume, as you may see from the formulas, to be a full order observer at this point. And I have a controller here, which for this diagram, I'm assuming to be a static control law, U equals K of X plus E, where E is the error that the error with which the observer reconstructs the state X. So if you assume that the observer is robust in the sense that I just described, then you also need to characterize the robustness of this controller with respect to the resulting state estimation error. And for this, it is a standard assumption to assume that the controller is input to state stabilizing with respect to the state estimation error. So if you act on the plan to the control U equals K of X plus E, then the plan satisfies the ISS estimate with respect to this error E. So this property is quite well studied in the literature. I list here several references for it. It's known to be quite difficult. So it's only for some special classes of systems and for some special controller designs that you can prove that you can have this property. Nevertheless, for the purposes of this talk, I'm going to take it as an assumption. And then if you have these two conditions in place, you can show via a cascade argument that the closed loop system is quasi-ISS in the sense that, this formula may look a little bit complicated, but it's basically saying that the overall state of the system, which includes the planned state X and the observer state Z, satisfies an ISS estimate with respect to the disturbance. And again, this estimate is not global, but semi-global, if you will. So for any size K of the state in the input, you have the corresponding functions beta bar K and gamma bar K, which validate this ISS condition. So the message here is if you design the observer to be robust in the semi-global sense, and you have a controller that's robust in the more standard ISS sense, then when you interconnect them together, you have, again, this robustness to disturbances in the semi-global or quasi-ISS sense, which is not really surprising. And so one application that we worked out that I'll mention only quickly because perhaps some of you may be more interested in the other applications that are coming later. But we worked on the case where the disturbance generator is a quantizer. We have quantized output feedback, and it's the quantization that causes the disturbance. So you have this quasi-ISS property from the previous slide with respect to disturbance, no matter what the disturbance is. But in this particular case, the source of the disturbance is quantization. So I take h of x to be my output, and I apply a quantizer to it, where a quantizer is geometrically represented by partitioning a bounded region in the output space into finitely many subregions and choosing a point in each region which corresponds to the quantization value. There's one more point that corresponds to a saturation value that covers the complement of this square. And so D in this case corresponds to quantization error. And you can upper bound that by noting the largest distance between quantization point and any other point in the corresponding region maximized over all regions. We call that delta. And so as long as you're inside the square, and I assume that the size of the square is denoted by m here, then the quantization error will be upper bounded by this quantity delta. And then we worked out the result, which says that based on the size m of this bounded quantization region, you can compute a constant k and the upper bound on the quantization error as long as the initial condition, such that, first of all, you guarantee that the state and the input remain bounded by k. And then you prove that the state of the plant as well as the observer state are ultimately bounded by some nonlinear gain function of your quantizer resolution delta. And if your quantization is fine enough, then this bound will actually be smaller than the initial bound on the state. So that means you have a contraction. And if you want to actually achieve asymptotic stability, there is a technique known as dynamic zooming. By zooming in and refining your quantization, you can in principle achieve asymptotic convergence to zero using this result. So if you're interested in this quantized output scenario, you can look up details in our transactions paper that I cited at the beginning of the talk. So let me now go to the last part of my talk, which is about two applications to robust synchronization. So I'll give two examples that are united by this common framework of connecting robust synchronization with this notion of QDES observers that we've developed. So the idea here is, let's say we have a leader system, and I assume that it's given in this form. So again, I have a splitting of the state into two components, x1 and x2. Here I don't have control input in this setting. So it's an uncontrolled system that is the leader. The leader sends information about x1, only x1. This information gets corrupted by disturbance before it reaches the follower. And the follower tries to synchronize with the leader. And the dynamics of the follower that I'm displaying here is a copy of the second portion of the dynamics of the leader. So the follower may be physically homogeneous with the leader. So they may also have the same state space dimension as the leader. Therefore, there may be some other dynamics on top here, but I'm ignoring those because for the purposes of synchronization, x1 is statically available through my measurement. So my observer problem is only consists in building observer for the second portion of the state of the leader. And so accordingly, I focus on the synchronization error, which is the difference between Z and X. And my robust synchronization objective, I'm defining it on purpose to be compatible with what I've talked about so far. It's that for every K positive constant, I should have this ISS estimate from disturbance D to synchronization error E whenever the leader state does not exceed K. So for any compact range of values for the leader, as long as the leader doesn't get away too far, the follower should be able to synchronize, and the synchronization error should degrade gracefully for bounded values of the disturbance. So when the disturbance is 0, they should synchronize in the usual asymptotic sense. But for small disturbance, there should be accordingly small degradation of the synchronization objective. So this is clearly equivalent to saying in my previous language that the follower acts as a reduced order QDS observer for the leader. And we have a sufficient condition for this from before, which is encoded by this Lyapunov function V of E, which satisfies some appropriate bound on the gradient, which satisfies this inequality, which is essentially saying that in the absence of the disturbance, the synchronization should be achieved in the sense that the aerodynamics should be asymptotically stable. And then there should be asymptotic ratio condition, which says that asymptotically the ratio of this function alpha 4 to this function alpha 3 should go to 0, which if you check, this is exactly what I was speaking about on the first few slides in this talk. So we have a way of checking this, which actually turns out to be applicable in the examples that I'm going to talk about. So the first example has to do with synchronizing power generators. I'm just going to go rather quickly through this because I don't have that much time left. But I have two power generators. The first one on the left here is servicing a load. And the second one is trying to connect to the first one. And this vertical bar here represents what's called a bus through which the two generators are to connect. So the model of the generator that we use is a reduced second order model. So theta 1 is the phase angle, omega 1 is the frequency. Here, L of t is the electrical load, which we take to be slowly varying in an appropriate sense. U1 is the control input. Physically, it corresponds to mechanical power applied to generator shaft. And we apply integral control to make the frequency omega 1 approach the desired nominal frequency. Now, the second generator's model is similar, except there is no load because it's not yet connected. What is being measured is the phase, but not the frequency of the first generator, and that's corrupted by disturbance. So you may think of this as a phasor measurement unit, which is subject to spoofing attacks or some other sources of additive disturbances to its measurement. So in this setting, the objective is to connect the second generator, and you can only do that when both the phases and the frequencies at least approximately match, according to certain specs that I'm not going into details on here. And what we checked is that with V equal to E squared, we do have VS from D to E, where E here is the difference between the frequencies. And so we can show that the frequencies will synchronize with the error that's proportional to the size of the disturbance. D1 here is the damping constant. Little k here is actually the gain in the integral control that we're applying. And there will also be additional term that captures load variation. So this is not completely trivial to work out, but this does work out. And then due to the phase shift, the phases will drift, so they will be approximately equal at some time. And at that time, we can connect the second generator. So there is also a more challenging case where the damping constant D depends on the phase, in which case we actually get quasi-DES and not DES from D to E, so it becomes a bit more challenging. And what we're also ultimately interested in is looking at the network case. So in the microgrid setting, you can think of this first generator as a stand-in for a network of generators servicing several loads. And the system on the left would then be an average system capturing the average of the dynamics servicing this average load. And then it would be a more interesting case where you're trying to connect another generator to this already operational network of generators. So that's something that we're working on. And just in a couple of minutes that remain, the second application example is the famous Lorentz system, which displays chaotic behavior for at least certain values of its parameters. So this is a system, for certain values of parameters beta, sigma, and theta, it displays chaotic behavior like the one I showed in the picture. And the measurements here are measurements of the first variable, x1, corrupted by the disturbance. And we build the observer here, reduced order observer, which is basically just a copy of the second and third components of the Lorentz system with y substituted for x1. It's actually a standard argument to show that the state of the system is bounded. You can use this quadratic Lyapunov function. And we are able to show quasi-DES from disturbance to the synchronization error using another also quadratic error-dependent Lyapunov function. And what we focused on in our paper that I cited earlier is on the case where the disturbance D comes from time sampling and quantization applied to the measurements of x1. And in that case, we're able to derive a concrete bound on the synchronization error, which depends on the data rate in the channel that causes time sampling and quantization. And the synchronization error is actually inversely proportional to the data rate, which makes sense. So as you increase the data rate, you also reduce the synchronization error. And you can check the papers that I cited for details of these calculations. So I'm essentially done. This is the talk outline, just to flash it once again. So I talked about a little technical result on ISS. Then the main part of my talk was formulation and Lyapunov criteria for testing robustness of nonlinear observers to measurement disturbances. And I spoke about how this is applied to output feedback observer-based control, and also how it's related to the problem of synchronization robust with respect to measurement disturbances, and looked at two examples with some physical motivation. And so some future work that remains to be done. So for nonlinear quasi-DES observer design, we still need to understand better how to identify classes of systems to which our conditions apply and how to constructively design observers for these systems. For quantized output feedback control, a big issue is to be able to relax the ISS controller assumption, which, as I said, is quite restrictive. In robust synchronization, I'm basically looking for other examples that I might be able to handle using the framework. So if you have some ideas, please don't hesitate to let me know. And you can find all the papers I mentioned at my website. And with this, I thank you very much for your attention.
Thanks so much, Dr. Liberzon. So it was a great talk. So, all right, so we have about 5 to 6 minutes. Right now, basically, I am leaving the ball on you. You can ask questions in a couple of different ways. One way is you can unmute yourself. In the past, sometimes some people did that. So far, it didn't cause any chaos. Or if you don't want, again, session is being recorded, if you don't want your voice to be heard, you can directly send your question through the chat box, and I will be very happy to read your question to Dr. Liberzon. So, another way is, of course, you can always email to Dr. Liberzon if he is fine with him. Usually we have some questions, but sometimes time actually 50% by chance. Sometimes people are online shy a little bit, but sometimes asking questions. But we got one question. Okay, from John Cooper asking. I don't know if you can see it, but I can read it for you. Is there an analog to this technique for input disturbances?
For input disturbances. Okay, so that's actually a very nice question. So the setting that we have here, if I go back, maybe let's say to synchronization or to this diagram, right? So the setting here is that I have a sensor, and then the disturbance affects the sensor measurement, and then I have an observer that acts on that. So for focusing on observer design, we were mainly focusing on sensor measurements. However, if you look at the Lyapunov conditions that we have written down, at some point, when you go through the math, it stops being important where the error came from, right? So if you write down these conditions, or maybe there's a better illustration when I was talking about these Lyapunov-based conditions, right? So as long as the Lyapunov function satisfies a certain dissipation inequality, the disturbance appears here, but at this point, it's not that important where the disturbance actually came from. So I would say the short answer is that the Lyapunov framework in principle is applicable to disturbances arising in a different way. But on the other hand, I think some of the conditions that we worked out are specifically tailored to the observer design framework. And so it would have to be checked whether these conditions are still meaningful. But in principle, mathematically speaking, they can capture disturbances entering in different parts of the system as well.
Thanks a lot. So this was a question from John Cooper. Another question to me, will the video be available? It will be available probably within a version of the video will be available by tomorrow, I believe. We'll download from the WebEx website. Dr. Liberzon, I would like to thank you very much for your time and for your excellent talk. And unless there is no other question, we can end the session here.
I thank you very much, Tansel, again for organizing, and to the listeners, I'm very thankful that you took the time and were patient to listen to me. And I know that some of the details may be a bit overwhelming. So like Tansel mentioned, I'll be very happy to answer questions at any later time by email. Feel free to contact me, and feel free to also download the papers. And I think as Tansel mentioned, the slides will be available. So if later you go through them and some questions pop up, I'll be very happy to answer.
And thanks a lot, Dr. Liberzon. It was, of course, an honor to host you. And all right, thanks a lot. I also would like to thank everyone for their time. We had about more than 60 people. I am sure you enjoyed the talk. And our next speaker will be Dr. Ilya Kolmanovsky from University of Michigan on April 6th. We will send you an calendar invite and an email about this. And again, thanks a lot, Dr. Liberzon, and have a great rest of the day.
Thanks, everyone.
Sure, bye.